Right then, gents, week 2 of electrical power and drive systems. What we're going to do this week is we're going to have a look at the complex power flow and looking at how we can do some analysis of that using the complex number stuff. Mark did cover a little bit of that in his session last week, I believe, if you attended. Okay, we're going to talked a bit last week about power factor and its implications, about the fact that the supply authority penalise you for bad power factor. So we're going to have a look at the introduction of power factor correction and do some calculations around that. And then as the first part of me trying to split the session a little bit and doing something about the power systems towards the exam, also start to do a little bit about some motors. And I don't plan to cover every type of motor there is out there. The idea is I've got to cover a couple of 3 motors to a certain depth, types, and to give you an indication of the types of things and where you might look deeper when I asked you to write about some motors or an application for motors in the first assignment. Okay, so it's not about me teaching you everything that you need for that assignment. It's more to give you an idea of the key things that are important about motors when you're selecting them and how they work. Okay, so first of all, complex power flow. If we consider that we have to have this situation where we get the conservation of energy, all energy put into a system has got to come out the other end somewhere. Has to be totally balanced system to comply with conservation of energy. Therefore, the real power supplied by a source has to equal the sum of all the powers that are being taken from it. All have to add up. It's a bit of like a Kirchhoff's law type situation where the sum of everything adds up to nothing, in other words, because nothing going in, nothing coming out, it's just going round and round in a circle. Yeah. So the balance between the reactive powers must be maintained. Okay, so the real power supplied by the source, that's the watts, is equal to the sum of the real powers absorbed by the load, and the balance between the reactive powers also maintained. This means the total complex power delivered to the loads in parallel is the sum of the complex powers delivered to each, such that for the following circuit, we know that the apparent power S is simply the volts times the current for the whole system, and that's why it's measured in VA. So we can say that is the voltage multiplied by I1 plus I2 plus I3 in brackets, because the total current is all those 3 added together by Kirchhoff's current law. And then we can, if we want to, split that up into, multiply out those brackets and say that S is equal to VI1 plus VI2 plus VI3. However, it is a little bit more complex than that, because these 2 impedances are complex in nature. They got a real part, the resistance, and they got an imaginary part, either the inductance or the capacitance. Therefore, we need to do some complex calculations here. So, for the above circuit, there are 2 ways that we can, and I hope Mark talked about this last week, 2 ways we can express a complex quantity, and there's examples of both here. In this circuit, the voltage is expressed in polar form. A voltage magnitude of 1200 volts at an angle of 0 degrees. Okay, and actually That's the first mistake in my notes this week, because to be absolutely pedantic about that, it should be 200 volts, angle 0 degrees. I missed the units off. Okay. Z1, 60 plus 0J, that's in rectangular form. It's got a 60 ohm real part, no imaginary part. We could just write that as 60 ohms. That's a resistor of 60 ohms. Z2 has a real part of 6 ohms and an imaginary part of plus 12 ohms. Is that an inductor or is that a capacitor? It's an inductor, yeah. An inductor gives you a positive imaginary part. Z3 is 30 ohms of real, so that's the series resistor, and a minus 30 J or minus 30 imaginary part, that is the capacitor, yeah, it's the capacitor. So what we're going to look at here is how we can find the power absorbed by each load and what the total complex power is for this circuit. So that would be in the form of so many watts plus or minus so many J var, volt amps reactive. We can have it in that form, and then if we wanted to, we could turn it into the vector form, which would be S in VA, yeah, at a particular angle. All right, everyone happy with that so far? So how are we going to do that then? How are we going to find out all these powers? Let's go back to slide 2. In the case of this circuit, is not that bit there gives us the power for Z1. This bit the power for Z2, and this bit the power for Z3. Yep. So the voltage is the same for all of them. So if we find all three currents and then multiply each one by the voltage, we'll get the three powers, and we can then add them all together to get the total. Yeah? So, how do we calculate I1 then? Silence. I is equal to V over Z1 in this case. Our impedances are in rectangular form, so what's 1200 volts angle 0 in rectangular form? Sorry? Yeah, it's just 1200. Yeah. And Z1 is just 60. It's got no imaginary part. So it's 1200 over 60, which is 20 amps. Yeah. No J part. I2. Here it gets a little bit more difficult. V over Z2. That's 1200 over 6 plus 12 J. How do we do that? I don't want to convert the bottom one to polar form. Do that calc on a separate page. 1200 over 6 plus 12 J. What we have to do here, the process is, we have to get rid of the complex part in a denominator. So we have to multiply the top and the bottom by what's called the complex conjugate of that. That's the same number, but with the sign change. So we do 6 plus 12J multiplied by 6 minus 12J. And if we do that to the bottom, we'll have to do it to the top as well. Okay? So we need to multiply these out. 1200 times 6 is 7200, and minus 12 times 1200 is 12 12s is 144 for a start. 144 and 2 zeros, I would make it. Am I right? Yeah? J on the top. On the bottom, you have to do 6 6s are 36. Yeah, I'm coming to that in a minute. 6 times minus 12 is minus 72J. 6 times plus is plus 72J. That's why the imaginary term disappears. And then 12 12s is 144. Minus 144 J squared. Yeah. Now, these two cancel each other out. Yeah. So we end up here with 7200 minus 14400J on the top. And we've got 36 minus 144 J squared. And J squared is minus 1. Yeah? Yeah. As Joe quite rightly said, to do that, to multiply that, or to do that bottom bit, you just do 6 squared plus 12 squared. That's always what it is. Because the minus 1 cancels out the negative that you get in the middle here. Because J squared is equal to minus 1. Alright? Yeah? So if you, all you need to do when you do that bottom line is add the squares of both these two numbers together, and you've done that. So what is 6 squared plus 12 squared? So we got 7200 minus 14400 all over, what was it, Joe? 180. Yeah, and then we do that. 7,200 over 180 is, we've missed the J out there, must have that J in there. Yeah, you do that division separately. So you do 7200 over 180 is sorry, 40, and 14400 over 180 is 80, is it? Yeah. Okay, and the units of that are amps. Yeah. So 40 minus 80 J amps is the answer that we were looking for I2. Yeah. I3. Right, gents, what we got then? There's obviously V over Z3. Which is 1200 over 30 minus 30J. When you've done all the other mathematical jiggery-pokery with that, what do we end up with? Before you divide it through. Yeah, yeah. 36,000 plus. Yeah. Yeah, because you've got to multiply by the complex conjugate of that will be 30 plus 30J. So it must come out positive. And that's all over 1800. And then when you divide that through, you end up with units are amperes. Yep. Okay. So there are three currents, I1, I2 and I3. Yeah. What we want to do now is calculate the power dissipated in the resistor. So power in the resistor, we'll call it P1, is, how can we calculate that? V times I1, so that would be 1200, so the voltage, times 24,000 watts. Yeah. P2 V times I2 1200 multiplied by 40 minus 80J. We're going to have to put that on the next line. It's going to have to 48,000 minus, yeah, and we'd have to write that like this: 48,000 watts minus 1200 times minus 80. 96,000 J. Didn't think that looked like enough. can't be. Yeah, because that's 48,960. 1200 times 40. 96,000 is right. J var. Yep. So there's a power with a real and a complex part. The real part is the watts. The imaginary part is the reactive power in var. And then P3 is V times I3. That's 1200. Yep. On the end is var. So the real part, Daniel, is watts. The imaginary part is var. 1200. I have to tell you. 1200 times 20 plus 20J. I make that 24,000 watts plus 24,000 J var. Yeah, everyone agree? Okay. Therefore, the total power, P total, is all these watt ones added together. So just add up 24,000, 48,000, and another 24,000 watts. Must be 96,000. And then minus 96,000 plus 24,000. J var. Okay. If you now do a polar conversion on that, you'll get the VA, S in VA, yeah, plus you'll get the phase angle. A 120,000 angle minus 36.8 degrees VA. That VA should be not there, but VA minus 36 point what degrees. Okay, so that gives you your apparent power in VA, and that will tell you what the phase angle is. You could then do a cos on that phase angle and get what the power factor is for that circuit. Okay? Everyone happy with that and happy they could do that maths? Yeah? Alright? And that's just a slightly different way towards the problem to what we looked at last week, and that's one where we've got the ohmic values of the real and imaginary part of each component. Alright? If you do the cos of that angle, that's the power factor. Yeah. It's always a number less than 1. Well, the maximum it can be is 1. You try and get it up as close to that as possible. Yeah. It's the percentage of how much power you're delivering or current you're delivering from the motor has actually been converted into real power in watts. Yep. Okay. So, a little bit more about that now as well, Richard. Right. Last week, power factor correction. Last week, we discussed a little bit about how low power factor results in a power line having to pass more current for a given load. Yep, so just to, in summary of that, if this is our power, the real part of load, if we've got bad power factor, a steep angle, the length of that line in current terms is much longer than if we had a much better, higher power factor down here. Okay, and the supply authority will penalise you for poor power factor, because if they have a lot of loads with bad power factor, they can't supply so much power down the same line, because they can't, that current is higher in that one than it is in there for the same power. And they can only charge you for the watts, they don't charge you for the VARs, but they do in a roundabout way because they penalise you. They do that by charging you a proportion for your maximum demand. So consumers can improve poor power factor presented by high level of inductive load, and this is where it comes from mainly. There's high levels of inductive load from transformers, motors and so on that you have in industrial situations. By introducing some power factor correction. So inductive loads, actually we say they absorb or draw reactive power from the circuit. Capacitors work the opposite way. While in inductors drawing reactive load, capacitor is given some back. And that's just about choosing an arbitrary direction, because well, they both take some and they both give it back, but at opposite times. So when the reactive load is asking for power to magnetise it, the capacitor is doing the opposite thing and giving some back. Alright? So power factor correction involves introducing a level of capacitance into the circuit, which is said to provide reactive power to the source and go some way towards counteracting the reactive power drawn by the inductive load. Now, there is no attempt to try and achieve a power factor of 1. One reason is the law of diminishing returns. As you get closer and closer to unity, it's not linear, the amount of capacitance that you need to add to get closer and closer to unity power factor. The other issue about unity power factor is resonance. And in a series resonance circuit, which you don't come across too often, but we cover that in electrical principles. If you remember, you can get some very, very high voltages produced across the capacitor and the inductor when you experience resonance. What happens in the generally found parallel circuit if you achieve resonance is you get circulating currents that go around the parallel paths that aren't actually coming in through from the source. And these are the high currents generated by the inductor. Okay? So you do not want that at all, particularly in a high current, high voltage mains system situation like the national grid. Okay? So you don't try and achieve unity, but we try and achieve improved power factors from, let's say, the average 0.6 for a motor. Try and get your overall power factor to 0.85 or 0.9 in terms of what the cause of the angle is. Okay? So, reactive loads and power factor. If this is our reactive load with quite a low power factor, quite a steep angle here, no particular one, but it's got quite a steep one. We're delivering a certain amount of watts that we can charge for as a supply authority, but we're drawing quite a high reactive load in terms of Q inductive. If we add some capacitance to that circuit, i.e. we draw some QC, that's acting in opposite to the QL up there, we end up with what I've termed Q nu, which is the difference between the two. It's QL minus QC. It has the effect of pulling this line down that way and reducing the angle. The number of watts is exactly the same. Because the length of that hypotenuse line must have shortened, the voltage hasn't changed, therefore the current must have dropped. Yeah? So by reducing that angle, by introducing some capacitors into the circuit and reducing that angle, I've actually improved the power factor and reduced the amount of current needed to draw to power that exact same load. Right? Yeah. So, example of power factor correction. I'll go making a start on that question. Let's see how far we can get with that. Right, gents, where have you started then? Aye. Yeah. So I1 is I2 all multiplied out, that is. But be careful, that ain't ohms anymore. Yeah, that's just a complex number now. Alright. And the bottom here is yep. Therefore, P1 is that's I1 times V, 200 times 2 is 400 watts. All pretty easy standard stuff so far, yep. P2 is bored in. P2 I2 times V that's 800 watts minus 1600 J var. Yeah, the J is important. Okay. What did the question say? Total real, reactive and apparent power. So the real power P is equal to 800 plus 400 equals 1200 watts. Q is 1600 var. Well, if you're going to do it like that, you must put the negative in front of it. Yeah. Sometimes, and that's not always difficult to recognise, but sometimes you can just strip that away. If you're only interested in the magnitude, you know, you're just interested in that number 1600. It's when that's combined with something else that you have to recognise the importance of JB in there and whether that's negative or positive. It's when you take it as a whole with a resistive and a, or with a power and a reactive power part that you need to be careful with that.
So one of them is try and put it,
yeah.
Take off the minus.
Yes. We're going to draw a triangle in a minute. Daniel, how do we do this then? Yes, it's you've got to take the total P, which we've said is 1200, yeah, minus 1600 J, yeah, VA, okay, and then we can convert that to polar form. What is it? .1 degrees will do. Okay. Now we can express that as this, and we got 1200 watts. Let's put 1.2 kilowatts. We've got 1600 var, 1.6 kvar. Yeah, and we got 2000 2k VA, and in there we've got an angle minus 53.1 degrees. Yeah. So that's where we are with this circuit. Yeah, at this moment in time. So we've done that first bit. We've calculated total, real, reactive and apparent power, and we've also found the angle. So the power factor is equal to what? Cos 0.6. Yeah. So you've got a 0.6 power factor for this circuit. All right. Total current flowing from the source. I1 plus I2. I1 was 2. I2 was 2. That equals 6 minus 8J amperes. Yeah. And then we convert that to, just convert that to polar because we want the magnitude of it really. Sorry? 10. Angle should be, shouldn't it? Minus 53.1 degrees. Because as we said last week, you can get the angle from any of the phasor relationships. It's going to be the same. Okay, so if you had all the currents and find the angle, you'll get the angle for the power factor, same as you will if you look at the power, the reactive power, and the apparent power. Okay? Next bit is the value of capacitance C required to reduce the power factor to 0.8 lagging. Right, so how are we going to tackle this value of capacitance to reduce power factor to 0.8 lagging then? What's going to stay, what do we know is going to stay the same? Voltage is going to stay the same. And the power, yeah, the load's not going to change. Yeah. So what we're doing here, where's my red pen gone? Oh, here it is. We've got this triangle. Yeah. And we've got this, what was the power factor? 0.6 in there. Yeah. We want to reduce that in there so that is 0.8 because of that angle's 0.8. Yeah. So we've got to introduce some XC in there like that. Effectively, that's pulling this line down that way. Yeah. So what we need to do, we know what this is. This is 1.6 kVAR. Yeah. If we find out what that is, Q new, we can then find out from that what this is, QC. Yeah. And how from QC can we get the value of the capacitor? Yeah, you've got to get to a value for the capacitive reactance, haven't you? XC, and then from that and the frequency, you can find out what the value of C is. Okay? So, carry on, have a go at that. Okay? And then, once you've done that, see if you can get the new total current when the correction is in place. That'll give you an indication of how much we're reducing the current from the original total current to what we're getting if we reduce or increase the power factor from 0.6 to 0.8. Right, so how are we going about this then? How do we find Q new? How are you doing, Richard? Yeah. .36 point. Yeah, so that's the new power factor we want. Yeah. And then how have you used that to find out what Q new is? Yeah, because that's that, and opposite over. I want to show whoever's looking at this where it comes from. The tangent of the new angle is the opposite Q new over the power, opposite over adjacent. Yeah. Therefore, Q new is tan 36.9 times 1,200. Yeah. You think to move the bloody board down on it. What did that come out at then, gents? Tan 6.9 times 1,200. What did it come out at? 901 var then. Yeah. Okay. Therefore, QC is QL minus Q new. So that was 1,600, wasn't it? QL. What did that come out at? $699 var. So our capacitor has got to provide the source with 699 var of reactive power. Yep. Is that where you've got stuck now? As to how to get XC out of this? You do eventually, yeah, but you but we've now got a new triangle, haven't we? We've got I'll have a new S, which we haven't got. This is 0.8 in here, cos theta. This is $699. All we're looking at here is the capacitor. This is QC only. Yeah. This line down here is the same, power. But we need to turn that. We need to find XC. What are other ways to find what is effectively a power? No? Yeah, we've got three ways we can get QC. That's either equal to I times the impedance of the capacitor, yeah, or I times, and the impedance of the capacitor is the magnitude of it as XC, yeah, or it's equal to I squared, yeah, or it's equal to V squared over XC, or it's equal to IC times V. So we know this. We just calculated it. What other thing on there do we know out of all those formulae? We want to know this one. Yeah. We know voltage. Yeah, so we can use that formula to find XC. That's what working out how to do all these calculations is about. What different formulae do we know to calculate all these things? We need to find one that we can use with what we know. So therefore, if QC is equal to V squared over XC, XC must equal V squared over QC. That is, what was the voltage now? 200 squared over 901. What will that come out as? No, we're interested in QC.
No.
Yeah, sorry, that's my fault. 699. So that's 699 there. Right, 200 squared divided by 699, what will that come out as? 57.1. What are the units, Keith? Can you remember? No, we haven't got capacitance yet. We've got capacitive reactance. We've done a V squared over power here. This is a power situation. Yeah, so that must be, that's V squared over, that's in ohms. Yeah. We also know XC is equal to 1 over 2 pi FC. Therefore, C must equal 1 over 2 pi F XC, which is 1 over 2 pi. What was the frequency of this circuit? Times 50 times 57.1. We should get an answer. Fifty 55.7 microfarads. Yeah. Times 10 to the minus 6, is it? Yeah. Okay. What else is left in the question? Calculate the new total current, is it not? Yeah. How could we get the new total current? We know what this Q new is. Just remind me what Q new was. 699. Yeah. So we got a triangle now of 699, 1200. 901, wasn't it? 901. Yeah. So we've got a new power triangle of 901, 1200. We know this in here is 0.8 because theta. Can't be less than that. Not possible. If we find S, yeah, we can find out the current, can't we? Because we can just divide by the voltage and get the current. So how do I find S here? Yeah, it's square root of 1200 squared plus 901 squared, which is 1500 VA. Something strange here. Therefore, nu I is S over V. It's the 1500 over, what's the voltage for this circuit? Remind me. 200. 7.5 amps. Okay. Yeah. So, by putting in this power factor correction, what was the original current? Just remind me of that. $10 amps. So we reduced from 10 amps to 7.5 amps by putting in a power factor correction. If you're talking about a whole load of big factory and you make that kind of improvement in the power factor, you're talking considerably more of an increase in current or decrease in current than that. Okay? Right, here we go. Okay, gents, three-phase induction motors. They're probably the most frequently found AC motor in industry. All motors really. Simple, rugged, low priced and easy to maintain. That's the induction motor. They run at essentially constant speed for normal loads. Speed control is relatively simple using modern inverter drives. Controlling the frequency. Consists of two main parts: a stator, the bit that stays stationary, and the rotor, the bit that turns. So, we can have a look at what's called the squirrel cage rotor principle. Yeah. We think of this like a ladder, okay? We got bars that are conductors and they're shorted together at their ends with more conductors to make a ladder, and we imagine that for the moment lying flat, so they're short-circuited by the two bars A and B. When you if you was to move a permanent magnet rapidly over the bars at a speed V, so that the magnetic field sweeps across the conductors, you'd induce a voltage that's given by the voltage E is B times L times V. B is the magnetic flux density of the field. L is the length of conductor that is experiencing that change in field, and V is the velocity at which it is changing. So the faster we move this magnet, the more voltage we get. The longer we make the conductors in the field, the more voltage we get, and the stronger we make the field, the more voltage we will get. That induced voltage E in the bars causes a current to flow around inside there, and it reacts with the field of the magnet and exerts a force on the bars in one direction or the other. Okay, so there's the induced voltage immediately produces a current, I, which flows down the conductor under the pole face, through the end bars, and back through the other conductors. So we get a current flowing in the bars of the rotor. Yeah. Because the current carrying conductor lies inside the magnetic field around the end of the magnet, it experiences a mechanical force called the Lorentz force. This force always acts in a direction to drag the conductor along with the magnetic field. So this conductor under here, the one that's in the field, is effectively going to have a force on it. It's going to try and drag the whole bar of conductors in the same direction. So in this case, if free to move, the conductor bars would follow the magnetic field to the right. Okay? Everyone happy with that? However, as the ladder of conductors picks up speed, the field would be cutting the conductors less rapidly. Remember that formula, E is equal to B, L, V. The size of E, one of the things it's dependent upon is how much faster, in this case, the magnet is moving than the ladder is. It's the relative speed between the two. Because to generate a voltage, that conductor's got to be experiencing a change in field. So if they're both moving at the same speed, the magnet wouldn't be cutting across the conductor. So the induced voltage would decrease as the ladder picked up speed. Okay? Consequently, the force on the conductor would decrease. If the ladder were to move at the same speed as the magnetic field, the induced voltage and current in the bars would fall to zero, meaning there would be no force on the bars and no movement. Okay? This means there will always be a difference between the speed that the magnetic field is moving and the speed at which the conductor bars move at. And we'll have more about that later. So it's a significant part of the way an induction motor works. Joe? Slip speed. Yeah, so we're gonna once we're in the motor actually going round and how it goes round, we'll talk about slip. But there's always a difference between what's called synchronous speed and actual speed of the motor, and that is what the slip is. And that's the reason why there will always be slip, because if they travelled at the same speed, you'd not create a magnetic rotor, and therefore it wouldn't turn. Okay, you're all okay with that? So that I found that, and I thought that's quite a good way to show how this works by laying it out flat like a ladder initially and imagining it like that. In a real motor, the rotor, this ladder is wrapped up on itself, and that's termed a squirrel cage rotor. So the bars go in slots, but the whole rotor is made up of laminated plates with slots in them, and then the bars are laid in the slots, and the ends are all shorted together with a ring. Okay? And I haven't gone into that detail, but they use different materials for the bars depending on what characteristics they want out of the motor. But if you need to study for your assignment induction motors. That might be some material you'll go out and find for yourselves. Okay? So in an induction motor, the ladder is closed upon itself to form a squirrel cage as shown above. In the real motor, there is no moving permanent magnet. We cannot spin the stator around the outside of the rotor. That would defeat the object. The change in magnetic field is replaced by a rotating field created by the three-phase electricity that we apply to three windings. So I'm now going to explain that. Okay, is anyone who's had the three-phase rotating magnetic field explained to them before? No? Yeah? No? Maybe? Okay. So, if we had a rotor that looks like this, and it's got 6 poles, okay, each of them have a coil of 5 turns on. So, if we look at the one coming in at A, we connect that to one phase. There's a bit of it there, it's joined together in the middle, comes out there and goes to neutral. That's one phase. I'm going to make no apologies for using old colours here. The blue phase on C, to there, across the middle, to there, to neutral. Yeah. And then, how do I get a yellow pen on here? If I do that, and go yellow, the old yellow phase is there, across the middle, to that one, and to neutral. So there's our 3 phases, all connected to poles that are effectively 120 degrees between there and there. Yep. So we got 3 identical sets of windings, A to N, B to N, and C to N, all 120 degrees apart. The 2 coils in each winding, when this winding A is energized with the peak voltage, it creates a north and a south pole on those 2, a magnetic north and a magnetic south. Yep. Now, with our 3-phase electricity, the red, the yellow and the blue, new colours are brown, grey and black. Right. They wouldn't show up as well on my slides as these, so I've gone old colours. Black is the new blue and blue is the new black. I never quite made that one out yet, but why we did it, but we have. Okay, so if you look here, the red phase is peaking. We'd have a field top to bottom. Then this peaks. Blue next peaks in the opposite direction. Then yellow peaks in that direction. Effectively, we've got a field that's moving around the stator. Yeah. So we've got a rotating magnetic field working inside that stator. So, in position 1 on the diagram, we've got a field. This is our rotor in the middle. That's what the field would look like, because the red phase is at plus 10 amps, yellow phase is plus 5, and the blue phase is yellow phase is minus 5, blue phase is minus 5. Go to position 2, and the flux pattern has moved to the blue phase being negatively 10 amps, going in that direction. We've got a field that way, it's pulled the rotor around 60 degrees. Yeah. On to the next bit. So flux pattern at instant 3, where the yellow phase has got 10 amps on it in a positive direction. The rotor's moved now 120 degrees from where it started. And then a further step along, the red phase has a negative peak. We've got the north at the bottom and the south at the top, and the rotor has turned a full 180 degrees in that time. Yeah? So this rotating magnetic field is pulling the rotor round with it. It's doing that because that's passing this current through the bars in that squirrel cage and magnetising the rotor. There's no electrical connection to the rotor whatsoever in this type of squirrel cage induction motor. Lastly, at position 5, we end up with the rotor there. Position 6, we end up with it there. And position 7 would be back where we started. So in one cycle of the 50 Hertz mains, this rotor would rotate once. Okay, that would be termed a 2-pole motor. Each phase has got 2 poles associated with it. Right. More importantly, you'd call that 1-pole pair. And again, we'll come back to that in a little while. Right. But that would be called a 2-pole motor because there's only 2 poles per phase. Are you all happy with that? Can I move on? Yeah. So, synchronous speed of induction motors. Because the rotating field that turns the motor, or the rotor, has in an induction motor is created by 3 sinusoidal currents at a particular frequency, it must be true that the speed of the motor is related to the frequency of that supply. So that's how the modern inverter works, by making the supply a variable frequency supply. We change the frequency, we change the speed of the motor. A bit more technical than that, but that's the general theory anyway. Also, it's impossible to increase the number of pole pairs around the stator. What that has the effect of is changing the angle at which it moves for each cycle of the mains. So over here on the left, we've got our 2-pole motor that we just discussed. It's got 1-pole pair. In one cycle, that would step round, we've just seen, that would step round 1 full 360 degrees. Every step on that diagram had it going 60 degrees. Between phases, it moves 120 degrees. If we take that set of poles and place another set in between them, in one cycle of the mains, that wouldn't travel all the way round, it would only travel 180 degrees. Yeah. Therefore, we've effectively halved the speed of the synchronous speed of that motor by adding an extra set of poles in it. That would be called a 4-pole motor, and it would have 2 pole pairs. Well, you're mechanically reducing the speed of the motor.
So that's what it's just
Yep. Yeah. I would think so, yes. I haven't gone, for today's session, I haven't gone too deeply into torque. Talk a little bit about torque at the end, but not about what difference that makes to the torque. So but there's got to be a trade-off there. You've got more torque but you lost speed. Okay? There's only so much you can cover in an hour and a half. So as we've added an extra set, we've now only got 60 degrees between red and yellow, where before we had 120. Therefore, over that same period of time, we're only going to travel half the distance. Yep. So adding a set of poles halves the angle turn in a single cycle, and hence halves the synchronous speed. Synchronous speed of induction motor can be easily calculated from the synchronous speed little ns is 60 times F over P. And I'm looking up for that formula yesterday, a nice tidy version of it. I found a mistake in Bird's electrical and electronic principles. He'd missed the 60 off. What's the 60 for, Daniel?
60.
Why has it got 60 in front of F? What are the units of frequency? Where do they come from? Sorry? That's cycles per second, and we want the speed in RPM. So the 60 is the 60 seconds in a minute. Okay? So 60 times the frequency divided by the number of pole pairs gives you the synchronous speed. Okay? So for a 50 Hertz supply, a two pole motor has got one pole pair. Its synchronous speed is 3000 RPM. Yes. In the books I got, I've seen mention of 12 pole motors, 6 pole pairs, which is going to take that down to what, Keith? 3000 over 6. At 500 RPM, yeah. Alright? So for a 4-pole, 2-pole pair motor, they'll halve the speed to 1500 RPM. And they're quite common, 1500 RPM synchronous motors, probably the most common of all. Yeah? As discussed, so I'm going to talk about now is slip. As we discussed previously, the field in the rotor is created by the voltage induced in the rotor bars by the change in rotating magnetic field. And it's only changing if it's travelling at a different speed to the rotor. If they're both going together, then there wouldn't be any moving magnetic field relative to rotor speed, and therefore no induced EMF and no current and no field in a rotor. So if the rotor was to turn at synchronous speed, the rotating field would no longer cut the rotor bars. We get no voltage induced, no rotor field created, and therefore the torque would be 0. So in a practical sense, that doesn't happen. For these reasons, the induction motor never turns at synchronous speed. It is always a little bit behind. The difference between synchronous speed, ns, and the rotor speed, nr, is called the slip speed, or just slip. Yeah. More often expressed as a ratio, called the fractional slip. So that's ns minus nr over ns. Or as a percentage slip, which is that bit times 100 to turn it into a percentage. Starting characteristics of a 3-phase induction motor. If we consider first the motor with a locked rotor, so we lock the rotor up so it can't turn. Yeah, which is not a good idea. Please don't try it, because it won't last very long. The relative speed difference between stator field and rotor speed will be as high as it possibly can. We've got this rotating field going round and round and round, and the rotor's not moving at all. We're going to cut the conductors as fast as we possibly can, induce the biggest voltage we possibly could, and therefore a very high current in a rotor. It's going to get very hot very quickly. Yep. The rotor bar generated EMF, and hence the rotor current will be very high, several hundred amps typically. Yeah. So it's a technique about finding the parameters of a real motor is to lock the rotor, but you don't apply the normal voltage to it to see what's going on. You apply a much lower one. The force and hence the torque exerted on the rotor will be very high. So you imagine this locked rotor, then what happens when you suddenly release the rotor? It will rapidly accelerate in the direction of the rotating field. As it accelerates, the relative speed difference between the stator field and the rotor field progressively reduces. The motor will accelerate then until the torque being produced by the motor is equal to the braking torque that's trying to hold it back. So all the friction and the applied load that you're trying to spin, that's applying a braking torque to the motor. When the two are equal, it'll sit at a constant speed. Okay, unless you change the load, then it will either slow down or speed up until the equilibrium comes back. At no load speed, the percentage slip is small, usually less than 0.1% of synchronous speed. If we consider a motor run initially at no load speed, when a load is applied to the shaft, the motor will begin to slow down. That slowing down will have the effect of increasing the difference between the rotor speed and the rotating magnetic field speed, which will induce a higher rotor bar current. Yeah. Therefore, that will in turn have the effect of putting more force on the rotor and increasing the speed again. So it's self-regulating in a way, but it will increase up to a slightly slower speed than it was because of the braking force or torque being applied by the extra load you just put on it. So when I say that's a relatively constant speed motor, it's constant at a given load. Yeah. But it will vary slightly as you load it up. So the motor will not slow to a halt. The motor torque and braking torque from a load will reach a state of equilibrium at which the motor will then turn at a new constant speed. Under normal loads, induction motors run very close to synchronous speed. For large motors, 1000 kilowatt or more, at full load, the slip rarely exceeds 0.5 of synchronous speed. That's a big motor, that is, 1000 kilowatt. Was it about 750 kilowatts to the horsepower? I think that's a rough conversion, isn't it? So you're over 10 horsepower there, aren't you? Hang on, no, yeah. Over 1,000 horsepower. Yeah, that's a big motor. Yeah. For smaller motors, less than 10 kilowatts, at full load the slip seldom exceeds 5% of synchronous speed. This is why induction motors are considered to be constant speed machines, However, because they never actually turn at synchronous speed, they're sometimes known as asynchronous machines. So slightly out from synchronous speed. Torque speed characteristics can be quite important when you're looking at matching a particular motor type to a load, because how that's going to behave dependent on what your torque requirements are. Torque of a motor is dependent on speed, but it can't be expressed as a simple equation. So what you'll find is, instead of that, you'll find a torque speed curve, a characteristic that shows how the torque varies as the speed increases. In this case, up to percentage of what the synchronous speed is. So the curve below, that one, is a typical torque speed curve for a motor whose nominal full load torque is T. That's this line along here. Full load is there, full load speed is N. Okay. There's a term pull-up torque. That's the minimum torque during the run-up from stationary to the breakdown torque. It's the lowest torque experienced in that speeding up period. This breakdown torque is typically 2.5 times what the nominal torque is. Very quickly after that, if you keep applying much more load, you'll stall the motor and it'll stop. Because we get to this situation where there's no longer any difference between the rotor speed and the magnetic field speed, and there's no torque anymore. Yeah. Sorry? You keep applying load here, here's full load, now it's very rapidly going to start to fall off. So the starting torque is 1.5 times the nominal torque. Maximum torque, called the breakdown torque, is 2.5 T. Pull-up torque is the minimum that's developed whilst the motor is accelerating from rest to breakdown torque. At full load speed, the motor runs at speed N. If the mechanical load increases slightly, the motor speed will drop until the motor torque is again equal to the torque of the load. As soon as these are equal, the motor runs at a constant but slightly slower speed. Excuse me. If the load torque exceeds 2.5 T, breakdown torque, the motor will quickly stop. Yeah. Small motors, 15 horsepower less, develop breakdown torque at a speed of about 80% synchronous, and big motors, 1500 horse and more, attain breakdown torque at about 98% of synchronous speed. Now, I'm not a motor expert, but if I was going to guess, I'd say you want to run your motor somewhere in this region here, maybe, because you're getting lots of torque out of it. If you load it any more, you're in danger of stalling it. Okay, so you want to be running somewhere around where the breakdown torque is. But I ain't an expert. Okay, looking on within the information that I found I was using to develop this stuff, there's some information there about the rotor resistance and how it affects this torque speed curve. So they can make the rotor out of different materials so that changes the rotor impedance or the rotor resistance, and therefore changes the torque curve characteristics of the motor. The other thing they do is, in a real motor, the squirrel cage, the bars in it, are quite often skewed as well. They're not straight. And I've read some information, not in detail, but it's talking about it quietens the motor down. I don't know why, you didn't read the detail. Again, this could be, if you're going to be looking in your assignment work at induction motors, you probably want to start looking at some of that. This is an introduction. This is covering the basics. Yeah? Has anybody covered that before? In any kind of detail? Didn't think you would have. Don't really come into BTEC, does it? And that is where I plan to finish up today. Okay? On this. And then I was going to give you